As what you can see over here is that an LED is fading in and fading out. But remember, this is not an ordinary fading in and fading out using a PWM pin. We are using a normal GPIO pin. See, we have not connected it to the PWM pins. We have just connected to a D1 pin. So what is happening over here is that we are generating a PWM using a normal pin by just doing some math over here. We initialize some variables. We initialize a D1 pin, a normal pin, no PWM library. See, I have not even checked open the library tab. So we are not using any library. Then we set the frequency time, that is always equal to 1 by f. So it's a 5 kilohertz frequency. You can also change it. The library don't allow it. Then we set the duty cycle. This is our duty cycle command. These are some initial states. And then this is the main loop to repeat. It increments by 1. And then here we wrote a type of a function to control the delay, like to control the switching time of the PWM. And then we did for the on cycle, then we did the same for the off cycle. So in this way, we were able to generate a manual PWM to control the PWM, or for generating the PWM using a ordinary GPIO pin. So guys, hello guys, welcome to learning microcontrollers. In this video, I will tell you how we can generate PWM using GPIO pin using PIC16F877A. We will set the frequency and the duty cycle of your choice, and then we will use these settings to like fade in and fade down an LED to demonstrate to you that the circuit is working. So for this you will require minimum component, no oscilloscope, nothing is required. We will just be verifying the circuit that we have made previously using the PWM library with this one. So guys, let's get started. So first of all, let me give you how the PWM looks like. So this is our PWM pulse. This is the on time, then we have off time, on off, and so on. Now what is frequency in this? Now take a look here, one on and one off time. This is your frequency. Like I say, I want to set a frequency of 5 kilohertz, then it will be decided by here, but that will be the timing. Now how to convert it to time? Just time is equal to 1 divided by frequency. Suppose frequency we want is 5 kilohertz, then t is equal to 1 by f, t is equal to 1 divided by 5000. It will be 200 microsecond total on and off time. So for a 50% duty cycle, it will be like 100 ohm on, 100 microsecond on, 100 microsecond off. So let me tell you now, what is duty cycle? The next question, what is duty cycle? Now for 50% duty cycle at 200 microsecond means it's a frequency of 5 kilohertz. Now if you want to change the frequency, then just change this 5 kilohertz to this time, this total time 200 to 400, whatever the value you want. Like lower the value, higher the frequency. So guys, for 50% duty cycle at 200 microsecond means at 5 kilohertz, high time is equal to 100 microsecond like this, and low time is equal to 100 microsecond like this. Then this means that your duty cycle is now at 50%. So your LED is like half on at 2.5 volt. Similarly, for 10% at 5 kilohertz, it will be 20 microsecond on and 180 microsecond off. So your LED will be at 20% of the applied voltage. Like for the 5 volt, it will be like, I think 1 volt. And for the 20%, it will be 40 microsecond on and 160 off. For 30, 60 on, 140 off, and so on. That is how you set the duty cycle. Now this is a very simple thing. Now this will be our hardware. This is our PIC16F877A microcontroller having 40 pins. It's a DIP version. And this over here is our simple LED. LED have 2 pins, one longer, one shorter. Shorter is always the ground, longer is always the power. To connect it with the PIC, you use a resistor. This is a current limiting resistor. I suggest you use a 220 ohm resistor. It's a good value. Now guys, let's do the connection. Connect the ground pin directly with the ground of the PIC. For the longer pin, that is a power pin, connected to the one end of the 220 ohm resistor like this. From the other end, you can connect it to any available digital input output pin. We are going to generate the PWM, and right now, unlike before, I'm telling you to connect it to any available digital input output pin. So that's the beauty of using this technique like this. So we will be using pin number D1, that's fine. Now let me introduce you to the hardware before we move on to the micro. So guys, this is our hardware over here. As you can see, this over here, one of these LED only will be used. Behind is the PIC16F877A, and behind is our PIC3 programmer tool, and rest is just a trainer board, so don't get confused by it. So guys, let's get to the MIkroC for PIC. This is our MIkroC for PIC. So on the left side, you can see in the file you have new, and I also have a lecture on this software as well. So you can just go and see that lecture how to download and install this for free. So, and totally legal widget from the official website. Click on new project. This window pops up, new project wizard. Click on next, write the name of the project, PWM managed generation tutorial by learning microcontrollers. This is the name I wrote. You may write any name you prefer. Select the microcontroller. I have PIC16F877A and the crystal is 20 MHz. Click on next and finish. So guys, this window pops up. Before you do anything else, first of all click on save to save your work. Now guys, we know the pin we have selected is D.F1, that is port D, pin number F1. So declare it as an output pin. Write this command trace D.F1 equals to 0. This register is a direction register, D is the port, F1 is the pin name, 0 means the pin has been declared as output. By default, we want the LED to be off, port D.F1 equals to 0. So by default, the LED is off. Give some initialization delay, not necessary, but I always suggest you give it in the one-time loop like this. Now we go to our forever loop, while 1 like this. Forever loop starts here, ends here. Now guys, as per our presentation as well, you can see here, let's close this one. Okay, as you can see over here, what we saw is that this, for the PWM generation, we need the pin to go high and low, high, low, high, low, high, low, high, low. So we write this over there to start our programming, because this will be a difficult code, but I hope you guys understand it. So first of all, this pin goes high, and then it have to go low. And then what decides the duty cycle and the frequency is the delay in between. So we need a delay here, and delay should be in microseconds. So we use the same frequency that we have set in the presentation, that is 200 microsecond equals to 5 kilohertz. Now suppose I want to generate a duty cycle, and I go back to the presentation to show you that if the duty cycle I want to set is 10%, then 20 microsecond on time and 180 microsecond off time. So let's do that. Okay, first we generate the 100% duty cycle, like it should be on 100%. Then we do not need the delay for the off time, and the on time will have all the time, that is 200. Like this, I build this code, it's built, and I run this using the PIC16 programmer tool. This is the PIC16 programmer tool. I also have a video on that. Please go check that, how to download and install this and use it. Click on file, import. This is the file we just created. Click on write. Okay, the file is being written. Let's get to the hardware. Let's see, do the LED glows like it should glow? Okay, we power up the circuit using PIC16 programmer tool like this. Okay, it is glowing at maximum brightness. This is the maximum brightness. Now we try to change the brightness. See, if we set the duty cycle, now to set the duty cycle, what our presentation said is that we have to play with these two delays. So if I want a duty cycle of, go to the presentation, of 10%, then the high time should be 20 and off time should be 180. So let's do that. So it is 20 and it is 180. So the LED should be dim now. Let's see, do the LED goes dim or not? Okay, this is the PIC16 programmer tool. I click on write again. Let's go to the hardware and see what happens. Okay, it is working. The LED has dimmed greatly. So LED is very dim now. So you can see the difference, a great difference. So this is working. Now this is working fine. Now let's do some other math. Now if I want to control it, I want to control this. Now the problem is that we cannot change this delay. Either use a timer or I give you another technique better than the timer, because timers are also very limited. So we suppose I write here an integer. I take an integer, I call it delay 1 or okay, integer, I call it duty. Okay, now if I copy and paste this duty over here, now this will be the problem. I build the code, see it gives an error. It only allows this if I use a constant integer duty. Now it may allow it, but the problem will be that, okay, constant integer equals to 100. I give a value. Now see, it's working, but the problem is that if I want to change this, then this is a constant, it cannot be changed. This is useless because I want something which I can't change over here. Like if I connect a potentiometer to control the PWM, like I want to fade in and fade out an LED, or I want to control the servo motor, then I need something here and I want to control these duty cycles. Then how I am going to do that? Now to do that, I show you a technique. You do not need the timer or anything. So let's do that. So let's bring it back. That was 20. Okay, now what we do is that first of all we should write a do while loop for the delay. We make a function here. You can make a function later on. Do while, do after and while after the delay. For both the delays or how many delays you may use, it is just to replace the delay with something which is controllable, like this do while. Now inside the do while we will have a variable called, we take a variable called counter for the high part, and then we need a variable to set the threshold, that the maximum when the loop gets terminated. This will decide when the loop gets terminated. This will decide the repetition time. So we have two variables for the high part. So now make it 1. Our step, this is the resolution, like the minimum we can go is 1 microsecond delay. So right now we have 200 microsecond frequency. So this means that we can go 200 steps. If you can go even below that, if your microcontroller allows it, then that will be even better. You will have more steps. So right now we will have 200 steps. So what I do is that over here I write the first variable count h. This one equals to count h plus 1. With every repetition it increases by 1, and when it gets terminated, once it reaches the threshold. And now these two values we have to decide. Now I copy this. Now just make a function out of it, replace the other delay as well with this. And here we will have more variables. We do not use the same. We write variables for the low side as well. Just make it L, the low side, and LT, the low side, the threshold. So L and L and L and LT, low side threshold. Now same, now we have just replaced the delays. Now you can call it that these are the new delay parts. I call them delay for high side start. I write here high side end, and I do the same for the bottom low side. So this will remove your confusion. Like you can just make a function out of it, no issue. First learn what I'm trying to do here, or trying to tell you. Delay for low side end. Okay, now what we do is that we want a delay. Now for every repetition it will, like, delay is basically like you have to waste time. So as soon as this command is executed, delay basically, like if we have a 5 microsecond delay, it have to waste 5 microsecond. So in this way it will repeat like 5 times, because count is set to 1 and count h, we will define these values. So I write them here in the forever loop. I define these values count h. What count h should be by default equals to 0, starts from 0, and then I define the threshold. Now this will decide for what duty cycle. Like I want a duty cycle of 10%, so for that the value should be 20. And now for the low side also starts from this one. The low side also starts from 0, because we are just wasting time here. Now how much time we have to waste? It will start from 0, time counting, and then how much we have to wait? That is the threshold. We have to wait like 90 times. 90 times 1 microsecond means 190 microseconds. It will waste 90 times 1 microsecond, 190 times, sorry, and okay, 180 times, because 200 is the frequency. Now see that in this way we get exactly the same code again. Now this code is supposed to generate a PWM of 10%, because we have set it 20. So let's see what happens. We build this code. Oh sorry, just have to build one. Okay, just click on build. Now click on write. Okay, the new code is being written. Let's see it does the same. We are just organizing the code now. Okay, let it build. It's built. Okay, this is fine. We have the delay generated. Now we go back. Okay, Now try to understand what I'm trying to do here. We have the count high increments by 1, so this is the delay side, and it is terminated after like HT, that is the termination. Like after 20 cycle, like after 20 microcycle of delay is generated, it goes ahead, and then here we generate a delay, and count LT is 180, and count add starts from 0. So that's fine. Now if we take a look here, we can optimize this code further. Suppose I call integer f time, that is the frequency time, equals to 200. We know that frequency time is 200. Why? Because f is equals to 5 kiz. This means t equals to 1 by f equals to 1 by 5 kiz equals to 200 microsecond. So that is why I write 200 here, f time. Now if I want to calculate the load time, what I do is that I just have to subtract the whatever the value is from the high time, this value. So if I write here like this, f time minus this threshold, then we will always get the same value. Like in our case it is 180. So f time, that is 200 minus high time, that is 20, is 180. It will always be the same value. Now take a look at the beauty of this code now. Now this is our duty cycle. If you take a look, this is a duty cycle. Now this is always a duty cycle. Now if I want to generate a delay of 10%, 10% of 200 is 20. So I just give 20, or if I just make it 5, it will be even less. I build this code, let's give it 5 and try what happens. Okay, it's just 5. I write the code and show you that now the thing is we got more control over the code. To set the duty cycle, like the frequency, we have to edit this, and to set the duty cycle we have to edit this. So we can play with both the frequency and the duty cycle. See, it is very dim, so it is at 5, the minimum possible PWM that we can generate. Also, it will be a good practice if instead of setting the frequency over there, we set the frequency inside the code. So we can also change the frequency whenever we want in the code. The PWM library do not allow you to change the frequency like this. You have to reinitialize the PWM pin. So equals to 200 like this. Now we will also be able to change the frequency inside the code. Now you see that now what we do is that we have played with the code. Now what I want to do is that, like I have done in my previous videos with the PWM, that is a library. Now what we do is that we write a code in which the LED will start from 0 brightness, it will keep on going brighter, and it goes to the maximum brightness, then it starts again. It will be like LED fading in and fading out. So let's do that with a manual pin. Remember, we are not using any module, any library. We are just writing the code manually, purely writing our own library using a digital input output pin, and we are not even using the timers as well. So with any basic microcontroller you can use a PWM using this technique. So now let's write the code. Now as you can see, only this is the pin, this is the variable we have to change the frequency. This is the duty cycle. To change the brightness of an LED, we only have to change this to change the duty cycle. So we like go up, we write another do while loop, do, and bring this outside, because inside this loop we are taking the frequency to be the same. So I take it outside. You can play with the code, I will give you the code, no worries, and you can even modify it in a better way. And now do while starts from here, ends here. Okay, I write this bracket, I write while, and this will be the conditions. And now we need another variable for this do while loop. I write integer turn. Turn is an integer. Okay, so what happens is that as soon as this do while loop starts, turn equals to turn plus 1 like this, and then this count is now no longer only here, we also bring it up here. So by default when the code starts, it's always 0, and the value of the count is incremented by 1 because we want the LED to like go high, like the brightness should go high, and maximum brightness, then it will start all over again. So it increments by 1. If you change this value, it will go faster or something. So to make it faster, we add a delay here as well. This will make the code slower. To make it slower, we add a delay here, else it will be too fast. Okay, a 50 millisecond delay will be fine, or you can make it 10 or whatever you prefer. So now see that what we made, this is the main command now. Only this command decides the duty cycle. See what I just did, I simply changed this to duty cycle. Now we go down. Now for this main loop we have turn, and turn should not exceed the frequency time. This is our maximum, like whatever the frequency it should only go that much time. So after that turn must become 0, turn equals to 0. So it should like repeat. If you don't make it 0, then it will not be able to repeat because the turn value is already above it, so it will keep on skipping it. So that is what we are going to do here. So this is the frequency time, this is our code, and what we expect from this code is that we have our integers initialized. This is for the outer loop. We have the LED pin initialized for the manual PWM. We set the frequency, we set the initial state of the duty cycle, that is 0, and then our main loop increments by 1, and then our lower side is set, that is the frequency will start from 0, like we will start from 0 brightness, and this is where our duty cycle comes in, starts from 0, and with every repetition of the main loop it will increase by 1, and it will stay for at one step for 50 milliseconds. That is why we set this delay. So it will remain there at one step, like we will have 200 steps and each step will take 50 milliseconds. So after 50 into 200 milliseconds it will complete the whole cycle, and then it will start all over again. So let's build this code. It's built. I click on write, so the new code is being written. Let's get to the hardware and see what happens. Take a look here. It is getting brighter and brighter. See, it gets brighter, and the brighter, then it starts all over again. Now what I do here is that this delay I make it less. I make it like 10 only because it seems slower to me. Now it's 10. I go back. I click on write again. Okay, we wait, the new code is being written. Now take a look here. It has gone faster. It starts from 0 and then it goes brighter and brightest, and then it starts all over again. So this is just like LED fading in and fading out. But remember, we are not using any special PWM pin. It's just a normal GPIO pin that we are using. So you can do it with any pin. See, now this is the beauty of this code. So guys, I hope you guys learned something from this video. I will be making more videos on this technique as well. Like we will be using a potentiometer, we will be using this to run a servo motor, we will be using this with an oscilloscope as well to see the result and other stuff. So we'll be doing in the future. So guys, stay tuned. So we'll see you in the next lecture.